Okay, so hello everyone, this is Discrete Math. My cat does not like the fact that I just said that. He's going to go. And this is Discrete Math from the University of South Florida. I'm Scott Grizzard. Today we're focused on deep induction. So the cat Elvis has left the building here. Gracie is her name. Anyway, she's left the building. I'm going to close the door so that there's no noise from outside. And of course she left the tarp in a mess, so now it's all doing that. Hopefully that will stop. All right. Are there any questions? Grading continues on the test. Perhaps TA can give us an update on the grading status for the rest of the problems for the partial credit. Can we get an update on the partial credit for the grading for the test? He may not be watching the stream. Okay, so the test was Friday. I was very pleased with most of the grades. That was very good. You'll notice that it was very heavy on the old stuff as well. The final exam, there's 2 exams left, a test 4 and then a final exam. The test 4 happens the last Wednesday in regular class, and then I don't remember which day exam 4 is on. Are there any questions about anything else? Okay, so okay, so the status of the test grading is that the TA in question was dealing with calculus all day Saturday and family stuff all day Sunday, and has not gotten to it yet for partial credit. The test was out of 110 possible. It's out of 100. That's graded out of 100. There's 10 extra credit as always, if that was your question. Also, I did decide what to do about the extra point. The extra point, there'll be a thing that says so I'll post the thing, but it'll be very short, very brief, and it will come out next week. So you will be fine with that. Are there any other questions people were asking? Okay. So today what we want to go over is last time we started deep induction. And the example that we did was that for any positive integer greater than 8, n cents can be obtained with 3-cent coins and 5-cent coins. So that was the example last time. Now, today what we're going to do is something a little different. Today what we're going to do, so we kind of involved the principle. And the key thing I want you to get out of this whole bit about deep induction is that recursion and induction are connected, okay? And very much so. That when you see proofs by induction, especially deep induction, and only really deep induction, this is why we're skipping shallow induction. When you see proofs by induction, deep induction, what you're actually seeing is an algorithm involving recursion. And that's the thing that I want you to get out of this, that recursion and induction are the exact same thing, right? A proof by induction, by deep induction, is an algorithm by recursion. All right. So to go back to our example from last time, I had that n was greater than or 8. Now, if I chose anything like 11, 12, 13, I could call the algorithm, right? I had that it was true for 8, 9, and 10. And then for anything bigger, like 11, I knew it was true for 11 minus 3. So I could make a call, I could have a function that would evaluate the truth of, say, 11. And that function would say, well, is it true for 11 minus 3? All right. And that was the big idea. 1 to 5, how do we feel about that idea? So this is... So 1 to 5, how do we feel about this idea? That induction and recursion are actually the exact same thing. And that when I do a proof by induction, what I'm really doing is creating an algorithm for induction. So that's the big idea. So let's write that down. Oh, crap. I've got on my tablet, I've got a ruler hanging out, and how do I get rid of this ruler thing? Let me see. There we go. Okay, so let's write that down. We can get rid of the cat cam. She left. So that's this overarching principle that I want you to get from this whole thing that we're doing. A proof by deep induction is really a recursive algorithm. Okay, so what we're going to do today, obviously there's no quiz to go over. What we are going to do today is we are going to discuss the idea that every positive integer n is divisible by some prime number. We kind of assumed this when we proved that there were an infinite number of prime numbers, but now we're actually going to like nail that down. And it's really, the point is not to prove that thing, although that's a nice proof. The point is to prove that, the point is to do examples of these things, okay? Then we're going to talk about the well-ordering principle. I should say that first thing we're going to do is we're going to state the principle. And then what we're going to do is we're going to talk about the well-ordered principle. And then we're going to do the quotient remainder theorem, the existence portion of the quotient remainder theorem, which we kind of just algorithmed out. Now we'll actually do the recursion bit for it. The next time we're going to talk about deep recursion and then writing an algorithm that will solve a problem called the Tower of Hanoi. And the whole point of this is to get to the halting problem, to get to things that are not computable, and then to get to things that can't be proven, the Gödel's incompleteness theorem. And we'll probably do liar. We may have already done that. And we'll probably do Russell's paradox. Someone look at how to spell Russell. There you go. And then we'll talk about Gödel's incompleteness theorem. And then hopefully we'll have enough time left over to talk about fun stuff like P versus NP. But if we don't, you know. So that's where we're going. Okay, so let's state this principle. It's an important principle to say. So let me pull out where it is. This is section 4.4, 5.4, box 1 on page 3. So the principle... This is kind of the big box theorem, the big box idea of this section. Okay. All right, so P is going to be some property. And it needs to be defined. It needs to be some property that's well defined. Not some property that's true, but some property that's well defined. Some property well defined for all positive integers. For all positive integers n. So an example of such a thing would be so P of n equals is the statement P of n is the statement okay. There we go. So the example of one of these is P of n is the statement n is greater than 10. Right? Now, this property is well defined for all of the positive integers. Right? It's false for P of 9 is false. P of 11 is true. But either way, the statement is well defined. Right? Either way, the statement is something that is either true or false, and not both at the same time. Right? This is a well-defined statement. How do we feel about that 1 to 5? That what I mean by P of n having some property and that it's well-defined. Right? It's not, so yes, so it could be something that's Boolean, has some kind of Boolean truth value. It could be something like that. But the point is that I don't care if the statement is true or false so much as I care that that makes sense. Right? The idea of P of n being greater than 10 makes sense for any integer. Not necessarily true for any integer, but the statement makes sense. If the statement can be evaluated as either true or false. Okay. Okay. Now, suppose the following two things are true. And the second one of these is a little tricky. So suppose there is some base case. Okay? So suppose two things. One, there is some posant A so that P of A is true. All right. So is everyone on board with this? So for example, P of 11 is true. Okay? And suppose, and this is where our example is not going to be very good. This is why we're going to need something stronger than our current example. The point of this was to have a state. And suppose the following. And suppose for every k from A to n minus 1, okay, suppose that for every k from A to p minus 1, p of k is true. And this is the part that's tricky. I'm taking this statement, and then I'm saying this right here. If it's true for every for every k less than n, that implies p of n is true. Right? So what I'm saying on this second bit, if it's true for every k, if it was true for every k, then it would also be true for n. If it was true for every k less than n, then it would be true for n. And that's weird. Then p of n is true for all n greater than or equal to a. Okay, so that's the principle of mathematical induction, right? So Boolean, as he said, which was true false, okay? The point here is not, and again, this is the confusing bit. If I assume that it's true for every k from A to n minus 1, and if I can show that therefore it must be true for n, then it must be true for all n greater than or equal to a. And I know that's a little weird, okay? But here's the point. My point is that I can recursively define an algorithm that would dip down eventually into my base case. Okay? So how do we feel about that, 1 to 5? It's a weird statement. Okay? But the point is that if I can dip down into a k, if I can reduce my argument to something that I can already show, all right, then at some point I would terminate the algorithm, right? If at some point I could reach back into my base case, I could get it. Now let's go here. let's go back to last time's thing. Right? How did that work? Well, suppose I can make change for 11 minus 3. Then I can make change. If I can make change for 11 minus 3, I can make change for 11. If I can make change for 12 minus 3, I can make change for 12. And so on and so on and so forth. So let's give this the number. Let's say I start with 18. Okay? Well, if I went back 18, it was true for 18. So I want to show that it's true for the number 18. Well, if so, I go back 3 spots and I say, okay, well, is it true for 15? Well, then I went back 3 spots and I said, okay, is it true for 12? And then I went back 3 spots and I said, okay, is it true for 9? Wait, it is true for 9. That was one of my base cases. Right? Therefore, it must be true all the way back up. Okay? And that's what I'm trying to prove. I'm trying to prove that there's a way to get backwards. There's a way to clip back. Yes, we're going to do another example. So, if I can move backwards, then I could show that if I could show that I can always reduce the problem to something that I've shown before, okay, then I can recursively just keep going back. So I will do another example in just one moment, but just out of curiosity, how do we feel about this right now? So 1 to 5, how do we feel about this? A little bit more explanation. Are we feeling any better or not? Okay. Okay. Let's do an example. This is, let me find the page number for you. This is 5.4. This is example 5.41 in the textbook. On page 302. Okay. Nope, 302. Okay, and it's called, let's see. It says the following. prove that every posant is divisible by some prime. Okay, in other words, for all posant n, every posant greater than or equal to 2. For all posant n greater than or equal to 2, there exists p prime so that n mod p equals 0. Okay. All right, so how do we feel about the statement? How do we feel about what we're trying to show? 1 to 5. So 1 to 5 on what we're trying to do. We're trying to show that for every positive integer greater than 2, I can divide by some. I can divide. There's some prime that divides evenly into n. Okay. There exists some prime number that will divide into n. Okay. And here's how we do this. First, the base case. Okay. Right. Well, 2 mod 2 equals 0, and 2 is prime. Right? Okay. Is everyone on board with this? 1 to 5, how do we feel about the fact that this property holds for 2? Right? That for some number, for if 2 is divisible by some prime number, namely itself. Okay. Okay. Suppose, and this is the induction step. Let's change this. Let's go this. So suppose for all k from 2 to n minus 1, k was divisible by some prime. In other words, suppose I could show for any k less than or equal to, so for any k less than n but greater than 2, this property holds. In other words, suppose that I could show it for everything beforehand. Now, I need to show that that would imply that it was divisible by n. Okay. Well, there's two options. The first is that either p is prime or p is not. I'm sorry, either n is prime. If n is prime, let p equal n mod p, and then n mod p equals 0, and we are done. Okay, so suppose n is not prime. So the first case is the easy one, right? I don't even need induction for that. If n is prime, it's divisible by itself, which is a prime number, and I'm done. Okay? So how do we feel about that little statement, 1 to 5? Just the fact that if p was divisible by itself, if n was prime, then it's divisible by itself and I don't have anything to prove. Okay. All right. Well, if n is not prime, then there is some posant A so that 2 is greater than or equal to A greater than n. And so that n mod A equals 0. Now, why is that true? What was the definition of being prime? It's not there. That was fun. That was one-time pads. There it is. Right, so do you recall this definition? Right. So, how do we feel about this definition? Do you remember this? 1 to 5, how do we feel about that definition? Remember? That was the definition. P is a posent, P is prime if P is greater than 1, and for all posents less than P, P mod K did not equal 0. So if I'm assuming that a number is not prime, I'm assuming that there exists some number 2 less than or equal to A. Yes. So if I'm assuming here, you're right. You're right. I need to flip this. Okay. Notice that A is less than N. So right. So what I've said is suppose I already have a way to show that it is true for every k less than n. Remember, that was my hypothesis. Suppose for all k from 2 to n minus 1, k was divisible by 5. In other words, assume that I have some way to get the truth value to show P is true. I have some way to do it. Okay? Right? I've assumed this. So now I'm below N. Right? I'm in a case that's below N. So I have some way to get there. Okay? And that means that all of this is just equal to 0. Okay. Okay. So how do we feel about this example, 1 to 5? Okay. All right. Let's do another one. Okay, so let's do another one. This is box 309. I'm sorry, this is page 309. Box at bottom. Show that yes. Now let's do less than or equal to. I don't want to start at 2. Okay. So for any positive integer n, and for any positive integer d that is less than or equal to n, show that the following is true. And this isn't positive integers, this is non-negative. I'm allowing 0. such that n equals dq plus r is less than d, and one other thing has to be true. And what was that? Oh, and r is greater than 0. That's enough. There's also some other conditions, but we just don't need it, the integer stuff. We don't want it for every integers. All right, we'll just leave it like that. So how do we show this? The key is to write it so that it reduces to an algorithm. So if we were going to write this, how would we write it? Inductively, recursively. How would we write this recursively as an algorithm? What would we do? Okay. We'll call this thing div. And we'd say div is going to take as an input in method, function, we'll say method. Takes as an input a posant in. And then what does it do? If n equals 1, what do I return? Oh, it takes as an input posant d. If n equals 1, d must equal 1. Return 0. Return q equals 1 and r equals 0. All right, now what do I want to do? Okay. You know what? Let's even get rid of the requirement that d equal. Let's even get rid of the requirement that d be less than n. This actually, it will make the proof messier, but it actually might make it better for you recursively. Okay. If n equals 1 and d is greater than or equal to, is greater than 1, return q equals 1, q equals 0, r equals 1. How do we feel about that, 1 to 5? what I'm doing is I'm thinking about a way to recursively do this. Okay. Now I'm going to write another condition. As a matter of fact, that condition is going to ditch one of these two. Not a condition, another step in my algorithm, right? So these are my cases, right? I got a nice little switch statement, if you know what that is. I've got if n equals 1, d equals 1, return q equals 1, and r equals 0. Indeed, let's expand on this base case. Let's say if n equals d, let's not do that yet. Let's say if n is greater than, if d is greater than n, return what? Return that. But now I'm kind of stuck, right? I'm sitting here, I'm trying to come up with a recursive algorithm, and I'm just sort of stuck. Is everyone on board with that? That I'm just kind of, I'm sitting here struggling, grasping with trying to figure out a way to write this recursively. Well, let's look at the induction. Let's try the opposite direction. Okay, instead of trying to build down like this, let's try a proof and see if we can write an algorithm based on our proof. All right. Let's do the proof. We're going to start with that same base case, though, except we're going to say the following. If n equals 1, and then we kind of got two cases, right? If d equals 1, return and n equals 1 times d plus 0. Okay, are we on board with that? Now, does everyone see that these two things map to each other? Okay, 1 to 5, how do we feel about the equivalence of those two statements? How am I doing on time? I'm doing okay on time. Okay. That this right here is the same thing in the proof as this is in the algorithm. That this right here is the same thing in the proof as this is in the algorithm. Everyone on board with that? Okay. Okay. Now, we've done this before. We did the algorithm for this before, where we simply subtracted the cards. Okay. So we know that there is this algorithm. I just keep recursively subtracting cards. But now we're trying to complicate something that we already know to show something. Okay. Now what I'm going to do in the proof is I'm going to reduce this to a base case. Okay. Now, if n minus d is less than 0, q will equal 0 and r equals d. Okay. In other words, if I wound up, if n is already less than, in other words, I can erase this and say the opposite thing. I could already say if if n is less than d, let q equal 0, r equal d, and we are done. I'm sorry, r equal n, and we are done. Okay, how do we feel about that one? Otherwise, n minus d is less than or equal to n minus 1. And the induction hypothesis. And by the induction hypothesis, I already have a solution for that. I'm going to call these P star and Q star. I'm sorry, R star and Q star. So the n minus d equals R star, I'm sorry, Q star, d times Q star plus R star. So, and then I'm going to do a little bit of algebra. I'm going to flip this over there. And I'm going to say, so n equals d times Q star plus d plus R star, which equals d times Q star plus 1 plus R star. which equals, yeah, so I'm done, because now, so let Q equal Q star plus 1, and R star equal R star. Quite fun. How do we feel about that, 1 to 5? So what I did was I scooped down. I went D back. Okay. Now this statement here maps to this one here. Does everyone see that? Now let's write the rest of our algorithm. What did I do here? I went back D. You know, these things are returning multiple things. I should really have method div q and div r, but whatever. This shouldn't be a q, it should be a n. So in other words, go back D and then add 1. Now I'd need an array thing. I need an array thing, right? So I'm going to need to like go back and fix my code and make an array. I should actually make 2 functions, right? One that gets the Q and one gets the R. And then add 1. But the point is that this right here, this step maps to this. And this bit here maps to this. Okay? Now, this is messy. I need to fix this. This piece of pseudocode ain't gonna fly, right? I need to fix this. I need to make it clear that this thing is returning an array, right? And I'm gonna have to do a whole bunch of programming to fix my thing. But the point is that it suggests a way to do it. the proof suggests the recursive algorithm to make it happen. So 1 to 5, how do we feel about the fact that there's a suggested algorithm built into the proof? And that then the proof suggests a way to make the algorithm happen. The algorithm suggests the proof, and the proof suggests the algorithm. And they're really the same problems. Now, I didn't pick the best example. Granted, first time teaching this, I don't have all the examples down, right? And no one would write this as, you wouldn't write this as recursion. You just run the division algorithm with a while loop. But the point is, I could write it as recursion. Okay. All right, I'm almost out of time, and you guys aren't convinced yet. So I'm going to spend another day going over this. I'm going to go find a really, really good example. It may be the Tower of Hanoi. It may also be the Euclidean algorithm, because you guys aren't convinced yet. That seems to be the way that this works. So I'm going to go find a much better example to try to make this clear. But it's very difficult. It's kind of a hard thing to grasp. Okay, it's this idea that recursion and induction are the exact same thing. And that here I've got a recursive algorithm that leads to an inductive proof, and an inductive proof that corresponds with a recursive algorithm. And that's the thing I really want you to get from this. And obviously this example, because of the messiness of the algorithm here, doesn't work for you. So I'll go look for another one. It may be the Tower of Hanoi. Which may mean I don't get to P versus NP, but oh well. Okay. So where we're trying to get to is the halting problem. I've already gone over the liar paradox once, but a direct consequence of that is something called Russell's paradox. And then hopefully we're going to get to Gödel's incompleteness theorem by the end of the class. We've only got 4 lectures after today, so I don't know if that's going to happen. Hopefully we might even get to the halting problem next time. So, with any luck, we'll get to the halting problem next time. We'll do Liar's products, get in Gödel's incompleteness theorem, and then we'll have 2 or 3 to finish on the last week of class. Hopefully, we'll have 2 for the last week of class to talk about P versus NP. That may be a little bit more edutainment-y than otherwise. Yes, I could. The problem is that this thing's going to be messy because there's going to be an array call in there. It'd be easier if I broke it up actually into two methods, but then it's messy recursion. So, yeah. Okay. Any other questions? Okay. There might actually be a nice recursive way of doing this that didn't just use the division algorithm. So I will see if that's up too. Any other questions? Okay. So that's it for today. I will see we didn't have to review a quiz, so we're done a little early. There are a couple of people taking makeups. If that's the case, stick around. Otherwise, I will talk to you all later.